For topic number 5, which is internal flow, we are going to use the system of a vomiting snake and then solve a problem for finding the force used to hold the snake in place if the flow inside the snake is laminar, if it is turbulent, and then depending on whether or not the result for laminar or turbulent seems more reasonable, we are to solve for the Reynolds number. And to do this, we use the density of water at 25 degrees Celsius found from handout number 4, and the following assumptions were made, which were that the flow is steady, that it's constant density, that it's incompressible flow, that there's no work, there's no mass entering the system, that beta equals 1, and that there's no entrance or exit effects. So the first thing that was done was the Bernoulli equation was used. That includes the friction loss term. And that was set up so that way it was everything that from simplified Bernoulli on one side and then the friction loss on the other side. Then the following equation for friction loss was used, where F prime equals 16 over the Reynolds number because it's laminar flow. And that value is plugged back into the equation for the friction loss to obtain the following term. After that, this was plugged into the Bernoulli equation to obtain this right here. Then the continuity equation was used to solve for V2 as a function of V1, and that was plugged into the equation above in order to get an expression that we could solve for V1 using the quadratic formula. From that, we found that V1 equals 1.056 meters per second and V2 equals 4.4 meters per second. Then a momentum balance was done to solve for the force, and the simplified momentum balance is F equals m times V2. So the force at that point is 74.3 newtons, or the force needed to hold the snake in place. Then, once we're assuming turbulent flow, we had to use this equation for F prime, and using that equation, we could plug that back into the friction loss term to get this, and then we could solve this equation using solver to find V1, which was 80.3 meters per second, and then V2, which was 164 meters per second. Using V2 and the momentum balance shown above, we could then find the force needed to hold the snake in place, which was 103,043 newtons. And since the force at laminar flow was much smaller and more reasonable to hold a snake in place that's vomiting than the force for turbulent flow, we could assume that the flow was laminar. Then in part C, we calculated the Reynolds number. And from this we found that the Reynolds number was 10.5, which is indeed laminar flow. So for topic number 7, which is flow through porous media, this is demonstrated through a water flowing through a pipe that is 50% full of donut holes. And to do this, we needed to find the density and the viscosity according to handout 4. And we wanted to find the pressure drop. And we were assuming that there is steady flow, that it's incompressible, that there's no work, and that ambient temperature is 25 degrees Celsius. So to find the pressure drop, we used the Reynolds number for porous media, which is calculated according to the follow equation and was found to be 1,119. Then, using handout 7, the friction factor of 1.8 was found using the curve that was there and the Reynolds number that was determined, and this was plugged back into this equation in order to find the pressure drop. And the pressure drop for this problem was found to be 448.7 pascals. Then to demonstrate topics 6 and 8, which is pump analysis and external fluid flow, we used a system of a fish that is spherically shaped that is swimming towards a pump that is powered by a generator that is pumping water towards it. And to solve this, we need to find the drag coefficient, which is what we're looking for. We need the density and the viscosity of water, which is found in handout 4. For this problem, we assume that there was steady flow, that it was incompressible, that the fish is a sphere, and that the ambient temperature is 95 degrees Celsius and that there's no friction. First, the Bernoulli equation that's including pump work was used, and this was used to solve for V2 in the pump, which was 17.32 meters per second. And this is the velocity of the water that the fish is swimming directly into. So as given by the problem statement, The fish is swimming at 20.14 meters per second before the pump is turned on, and then that would give us a relative velocity of the fish and the pump of 2.82 meters per second. This value gives us a drag coefficient of 0.416 according to this equation. And in order to see if this is reasonable, the Reynolds number at the velocity that was calculated was found, and that was found to be a turbulent value. And for turbulent flow over a smooth sphere, the drag coefficient is usually a constant 0.44. And since the calculated drag coefficient was 0.416 at a turbulent Reynolds number, this is likely a fairly reasonable calculation. For topic 9, which is compressible flow, we were determining the temperature inside of a man's mouth that is exhaling carbon dioxide at very high temperatures. So to do this, we had to assume that there was an ideal gas, but we're also assuming that the man's mouth is shaped like a nozzle. Compressible flow, steady flow, and constant specific heat at room temperature. Using handout 8, we could find the values for R, C, P, and K, which are used to find the C2. And with a given Mach number in this equation, we could find the velocity of the carbon dioxide leaving the man's mouth, which was 937.7 meters per second. Then an energy balance equation was used, and also the ideal gas assumption was used to say that the change in enthalpy equals Cp delta T. With this information, all variables were known in order to solve for the temperature inside the man's mouth, which was found to be 541 degrees Celsius. For topics 10, 11, and 12, which is all of the Navier-Stokes topics, we used a system of water flowing through an infinitely long vertical cylinder in order to solve for the velocity profile, and then when using numerical methods, the percent difference between the derivative found analytically and then the first derivative numerically using the forward difference formula. To calculate this, we needed to know the density of water and the viscosity of water at 25 degrees Celsius, which was found in handout 4. The assumptions that were made was that the flow was irrotational, that it was steady state, that it was incompressible fluid, that it was a laminar flow, that the fluid was Newtonian, and that the flow was fully developed. The first thing that was done was the continuity equation was used, and it was simplified to find that dv dy equals 0. Then a y component momentum balance was used, and that was simplified to find the following expression. Then that expression was integrated twice in order to find VR. However, VR has two unknown constants that had to be solved. And using the boundary conditions of symmetry, which was at r equals 0, dv dr equals 0, and no slip. So when r equals the total radius of the cylinder, then the velocity, which is at the wall, then the velocity equals 0. Using this, it was found that C1 equals 0, and C2 equals the following expression. Plugging in C1 and C2, we could find that this was the equation for the velocity profile. Then using forward differencing, in this forward differencing formula applied to our system and our variables, we could find, and also using the velocity profile determined here, we could find dv dr between the points of the radius at 0.05 meters and 0.0499 meters. We found that dv dr using forward differencing was equal to negative 274,152 meters per second squared. And then using the equation found here when solving the problem analytically, we could find that dv dr at 0.05 meters was, or at 0.0499 meters was negative 273,878 meters per second squared. The percent difference between those two values was only 0.1%, suggesting that forward differencing is a good approximation for this system at the specified R values.